certain way as we're talking about it. So sine and cosine are paired together because they're similar. And then the rest of the four actually have some similarities, but I still like to chunk it into twos because the actual physical graph, the tangent and cotangent look similar, and secant and cosecant look similar. There's some similarities of what we do with them, but the graphs don't look that much alike. So this first page is talking about a little bit about some of the reasons why tangent ends up looking the way it does. So tangent, the way we got it, the values on the unit circle was y over x, which was the sine value over the cosine value. And so whenever cosine was 0, we had a value of tangent that was undefined. Okay. So now if we're translating that to graphs, since there's some places where tangent's undefined, what that creates is something called an asymptote, which we've used that word before. Anyone remember what that is? It's like a value that's approached but never crossed. So whenever we did the graphs where they're broken up into little pieces, that was because of asymptotes. So when you look at tangent, the graph is broken up into pieces because they have all these vertical asymptotes because there's undefined values. There's values that are approached but never crossed. So if you look at the bottom half of that page, it shows you what tangent looks like roughly. I like this snip because it actually visually shows you the vertical asymptotes. When we're actually looking at the graph, the vertical asymptotes don't show up, but it is periodic. So again, the vertical asymptotes are happening at a certain interval. And again, the way the tangent works, again, whenever you're working with an asymptote, the graph will come really, really close to it, but never quite cross it. So that's why if you look at the tangent curve, which is, we call this a branch of tangent, it comes really, really close to this asymptote down here at the bottom, but it's never going to cross it. So eventually it'll kind of just go straight down. And then this one, it'll curve up, and again, really, really close to that next asymptote, but it can never cross it because this is an undefined value of the graph. There's no value for tangent there, so it's going to come really, really close to it and then kind of shoot up toward the top. Okay, so that's why tangent's shaped the way it is, because there's an asymptote every so often. And actually, every asymptote starts at, this should be pi over 2, every half pi. Okay, so that's why if you look where the red dashed lines are here, it's negative pi over 2, positive pi over 2, 3 pi over 2, which is 1.5 pi. So every asymptote from tangent starts off to be at every half pi. Okay. Now that doesn't mean that's where all the asymptotes are going to be ever, because again we can shift the graph left and right, so that'll shift our asymptote. But again, that's what kind of shapes the graph for tangent, is because it has all those asymptotes. It has a bunch of values it cannot cross, so it's just a little piece of the graph. Okay. Like I said, it's still periodic, so it still repeats. So it's just these little branches over and over. If you notice, the original period of tangent is actually shorter than the rest of them. The original period of sine and cosine was 2 pi. Actually, tangent only takes a single pi to repeat itself. So it only takes about 3 units before it goes on to the next branch. So this one has 3 periods of tangent. Okay. Again, typically what I want in the snip is 2 periods, so I'll just want 2 branches of tangent in your snip. Again, I don't need to see 1,000 of them. I just want 2 in your snip. So this one has 3 separate periods. For each one of the branches of tangent, that creates a separate period. Okay. And then, like I said, there's some other things up there. There's intercepts. Those are hard to measure because there's several intercepts along the x-axis. There's only y-intercepts. We could do that, but again, we're more worried about how it's shaped. So the big thing we're going to be worried about are 2 things I circled, are the period of tangent and the asymptotes of tangent, because that'll tell us how much it's kind of shifted. The height for tangent's hard to measure, because again, there's no real height to it because it goes up forever and down forever. So we can't really do amplitude for it. The phase shift, we actually lean toward the asymptote, because if you can see where the asymptote is shifted, then that's how the graph has shifted. So I said, as each one of the original tangents, asymptotes are at pi over 2. As we put numbers in and around tangent, that shifts the asymptotes, that shifts the graph. You can do a vertical shift, but again, that doesn't really show much for the graph, because again, the height won't really change. So really the only things we focus on are period and vertical asymptotes, because the vertical asymptotes will tell us the horizontal shift, and the period will tell us how often it's repeated. So, like I said, there's not as much to list about tangent as there was with sine and cosine, because they're of those asymptotes that kind of restricts the graph. Now you can still put numbers in and around tangent. Like I said, we still have a place where we can put A, B, and C. We just don't need to worry about the A and D as much. What A does, since it doesn't really have a height, it'll change the shape of the graph. So if you have a smaller A, the curve in the middle will be a little bit longer. So it'll be a little bit flatter curve in the middle as it's weaving through tangent. Put back so I can point to that picture. So this is a general slope of the curve. So like I said, if you have a smaller A, so like a half or 2/3, it's actually going to flatten this out a little bit more in the middle. So really that's what A changes. If it's a bigger A, it'll actually stretch out the A, so it'll actually look more like a straight line. So again, that's really what A does, is it changes the shape of the curve, but really it doesn't change the height, so we don't really worry about that. I wanted to see how the absolute value again. Because B is very rarely negative. So this time, period changes for us. So up to this point, when we did the period of sine and cosine, it was 2 pi over b. With tangent, it's just pi over b. Because, like I said, the graph for tangent is smaller, so it doesn't take as long for it to repeat. It only takes a pi to repeat instead of 2 pi's. So again, as you change the b value, and again, the b value is still the number of x, that still affects the period. Only how to find the period for tangent, that's pi over b. Vertical asymptotes start at every pi over 2. Now, like I said, that's the starting spot. So as we shift the graph left to right, that'll change our asymptote. So the way we measure how much it's shifted left to right is we measure how much the asymptote has changed. Okay? And kind of like what we did with phase shift was affected by C of V. Vertical asymptotes are also affected by C of V, but kind of in a slightly different way. We actually create a little equation for us to solve in order to find how the vertical asymptotes have shifted. So, like I said, really what's inside the tangent affects the vertical asymptotes. So what's here, the Vx plus C part, we're going to create a little equation for ourselves to solve so that we can find how the vertical asymptote has shifted. We take whatever's inside tangent, the Vx plus C part, and we set it equal to the original vertical asymptote, which is pi over 2. And then we solve for x. So whatever's inside the tangent gets set equal to the initial vertical asymptote. And so then we'll solve for x, and then whatever x is, that is where the vertical asymptote has shifted. So it starts at pi over 2, and it might shift to 3 pi over 2, or 10 pi over 5, or no, it's not 10 pi over 3. Okay? So again, we'll try to shift it, see how much it's shifted, because as the vertical asymptote shifts, that's how much the graph is shifted. So again, each original asymptote's at pi over 2. But again, as we change the numbers inside of tangent, that shifts the graph either left or right. So we can take that stuff that's inside the tangent, set it equal to the initial vertical asymptote, which is pi over 2, and then solve for x. So those are the two things we're going to find about the tangent graph. We're going to find its period, which is pi over b. And then we're going to find how its vertical asymptote has shifted, either left or right, by solving a little equation for ourselves. So there's only 2 things to list, and then snip 2 periods. For this, I think it's really easy to see 2 periods, because like I said, one little branch of tangent is 1 period, so I just want 2 of those in your snip. So if you look at the next slide, I've already pre-snipped all the graphs, just like I did before. Like I said, sine and cosine was a continuous curve. There was no breaks or gaps or holes in it. So that one was a little bit harder to measure 2 periods, but for all the ones that have asymptotes, it becomes a little bit easier to me because, again, it's broken up into pieces. So one branch is 1 period, So there's 1, 2 periods. You guys want me to show that in Desmos, or are you guys good with this? Okay, we've done Desmos enough. But like I said, for me, for tangent, snipping 2 periods is a lot easier than having to snip 2 periods for sine and cosine. Because like I said, that was a continuous curve. This is broken up into pieces, so I just need 2 pieces. If you get a little bit extra, that's fine. But do try to, again, use your zoom a little bit. If you need to, help you out to find 2 periods of that graph. Okay. Alright, period is originally pi over b. Where did we get our b value? Yep, the second number is number with x. So here, our b value is 4. So our period is and then our vertical asymptotes. So I'm going to abbreviate VA. We're going to take what's with the tangent, okay? I don't usually, or the book doesn't always put parentheses around it, but usually if there's something directly behind it, that's considered with tangent. So what we're going to do is take the stuff that's with tangent and set it equal to the original vertical asymptote for tangent, which, what was the original vertical asymptote for tangent? 5 over 2, yep. And so the original asymptote's at pi over 2. So this one's not, it has shifted a little bit because we have a 4x. So now we're going to solve 4x in order to figure out what the asymptote is for this graph. So basically, we're trying to figure out what this break is, roughly. So how do we solve for x?
Times by 2 divided by 8. I mean, yeah.
I mean, you can do it that way. I would just do it. We'll do it one step. Okay. Really, when we divide with fractions, instead of dividing by 4, what do we actually do? Divide by 4 over 1. Yep. So this is 4 over 1. So instead of dividing by 4, what do we really do?
Multiply by 1 over 4.
Multiply by 1 over 4. So then, what would x equal? 5 over 8. Yep. Either way you do it, you should get a vertical asymptote of pi over 8. So it's saying that this gap right here is about pi over 8. So this would be negative pi over 8. So every vertical asymptote is occurring at about pi over 8 instead of pi over 2. Let's stop first. We'll do another tangent real quick, and then we're going to switch to cotangent, because cotangent is very similar to so like I said, just to point out a little bit of what I talked about before, if you do have an A value, so like in this first graph again, so the curve, they had a little bit of a curve in kind of in the middle. As you make that bigger, notice this line's a little more straight, okay? The bigger the A value, the straighter the curve will get. So again, that's really the only thing that it tells you about the graph, because it doesn't tell you the height. So I could have it tell the slope of the graph, but again, we're more worried about how often it repeats, and then where those vertical asymptotes have shifted to, so you can see how much the graph has shifted. So I have 2 snips, 2 periods in my snip, okay? Like I said, it's really easy to see 2 periods with tangent. I just need 2 branches. Again, if you get a little bit extra here and there, that's fine. But again, try to really focus on just getting 2 periods. What's the period of tangent going to be for this graph? Pi over 3, yep. So the b value is still a number with x, so pi over 3 is my period. So now I want to see how much my vertical asymptote has shifted. So I take the stuff that's with the inside the tangent, the 3x plus pi over 4. So the last one we didn't have a c value, so we just have 4x. This one we actually do have a c value, so it's going to create a couple more steps for us to solve. What's the initial vertical asymptote for tangent? Alright, so now we need to solve for x. Again, there's two ways to do it. If you want to get rid of the 2 first, that's okay. I usually don't do that because a lot of people then forget to multiply it to both of these things. So I'm actually going to leave the pi over 2 and then solve for x by getting x by itself. So we have to get rid of the 3 and the pi over 4. Which thing should we move first? Pi over 4. So we're going to subtract that over. Okay, we are subtracting with the fraction now. Okay, when we multiply, we just multiply straight across. When we divide it, we take the top times reciprocal of the bottom. What happens when we subtract with fractions? You have to have a common denominator. Okay, what's a nice common denominator for our fractions? 4. Yep, this one's already a 4, and I can make this one a 4 pretty easily by multiplying it all by 2. So instead of pi over 2, it becomes 2 pi over 4. And then we subtract pi over 4. So then we subtract our pi's. So then 3x will equal pi over 4. And like I said, from here, if you want to multiply the 4 over and then divide by 12, that's fine. Or if you just want to divide by 3 right away, that works too. Either way, you should end up with pi over 12. Because I'm going to divide by 3, which when, instead of dividing by 3, what we have to do is take pi over 4 times 1 over 3. So take it times the reciprocal of the bottom. So that means each asymptote is occurring at every pi over 12.
Is it negative pi?
For which one? For this graph. In my step, yeah, it's showing the negative pi over 12 here. The pi over 12 would be over here. But again, it goes both ways. Are you watching?
Yeah. I didn't mean to do that.
Right. Shouldn't it be negative?
Open it.
Or-
So clicking on it.
Why would it be negative?
Pi over 2 minus pi over 4.
It'd be 2 pi over.
We should switch this to a common denominator. 2 pi over 4. And then subtract 2 pi minus 1 pi. Which is pi. This is like taking a half times or minus a quarter. You end up with a quarter. Any other questions about tangent? Okay. So I would switch gears and go to cotangent, but if you look at the cotangent, because cotangent's the reciprocal of tangent. So if you look at this graph, it's just going the other direction. Okay, it's shifted a little bit. So that one of the so the intercepts here are at half pi, and the initial vertical asymptote is pi instead. Okay, so it's occurring at every pi instead of half pi. So negative pi, 0 pi, pi, 2 pi, then we get 3 pi, and so on. Okay, but again, each branch of this is a period. So one branch, again, it takes less time for cotangent to repeat itself, just like tangent. So in this unique case, the period's pi, the vertical asymptote's also pi. So those are that's the initial period, and then the initial asymptote. So it switches a little bit with tangent, but again, it's ultimately the same idea. We're going to figure out how often it repeats as we change numbers in and around the cotangent, and we're going to see how much the asymptote has shifted. But instead of the initial asymptote starting at pi over 2, it's going to start at pi. So it changes our equation a little bit. Alright, so a couple blanks to fill out. So the period, again, is pi over b. And then every vertical asymptote starts at pi instead of pi over 2. So you will have to keep track of that for whether you're working with tangent or cotangent. Because we're setting equal to pi, most of the time it makes our equation a lot easier to solve because you're not initially starting with a fraction. That doesn't mean you don't have to work with a fraction. But again, setting equal to pi versus pi over 2 generally creates a little easier equation for us to solve. So again, we take what was with cotangent, set it equal to that initial vertical asymptote, and then solve for x. Alright, so again, 2 periods. This one, if you notice, I had to zoom way out because if you looked at my other snips, if you look at the scale, there was 1s in here. This one is going in between -10 and almost 15. Probably almost 12. So this one I had to zoom out quite a bit. So that's one reason why the graph looks a little bit different. So again, you'll have to still sometimes use your zoom feature so you can get 2 periods of the graph. But again, if you snip, you want 2 nice periods. Again, I got a little bit extra here and here. But again, as long as you have nice 2 nice full periods, that's what I want in your snip. Again, our initial period is pi over b. When you see something like this with x over 3, what's my b value?
1
Just 1?
over 3.
Oh, yep. So again, replace x with a 1. So the b value would be 1/3. So then what I do with my period, I take pi over 1/3. And I'm not going to leave it as a fraction over, or something over a fraction. So when I divide with fractions, what do I have to do? Multiply. So I take the top, which the top is just pi, times the reciprocal of the bottom. So what's the reciprocal of 1/3?
3.
Yep.
3 pi.
So it's 3. So again, a bigger period, that's why I had to zoom out. If you ever have something that has a bigger period, so bigger than pi in this case, that means that it takes a lot longer for it to repeat itself. So that's why I had to zoom out for this picture. So if you have a bigger period, you'll have to zoom out. If you have a smaller period, that's when you sometimes will have to zoom in to get a nice snip. Okay. So to do the vertical asymptote, we take what's with the cotangent, and we set it equal to its initial vertical asymptote, which what's the initial vertical asymptote for cotangent? Pi, yep. Now I just got done saying that usually setting it equal to pi instead of pi over 2 is a little bit nicer, but again I specifically did this one so we're working with more fractions, okay? That way we can do some fraction work together. So we need to get x by itself, so what do we need to do first? Yep, I'm going to add the pi over 4 first. I'm adding with fractions, so what do I have to have? Denominator. So what's my denominator going to be? 4. Yep. So I just have to adjust this first one. I will say every once in a while when you do this, you may have to adjust both of them a little bit. But again, just as long as you look at the denominators and try to make it easy for you to make it a common denominator. So instead of pi over 1, it's going to be 4 pi over 4. And we're going to add pi over 4. So once we have a common denominator, that's our denominator, so it's going to be 4. We just have to add up how many pi's we have. So we have 4 pi plus pi. Again, we're adding that over. Then we have x over 3 on the other side. How do we get rid of that 3? Just multiply. If it helps make a fraction, we're multiplying by 3 over 1. So multiply straight across. So that's going to be 15 pi over 4.
So how is it? On the other side, you technically multiplying x by 3, but you just simplify it down.
Yep. And then we just cross that. So then that means this value in here, and between our 2 curves, 15 pi over 4. What is that? Okay. Questions about that example? We'll do one more, and one like I promised where it's not quite so bad. So again, this one, if you look at my scale, or this, you can see the 1, you can see the -1. This one I think I zoomed in a little bit so I can get 2 nice periods in my snip. Now if you also notice, they're going the opposite direction now. They're going the direction of tangent. The only thing that changed is put a negative in front, it flips the curve. Okay? So sometimes cotangent will look like tangent if you make it negative. Same thing with tangent. If you make tangent negative, it'll flip it and look more like cotangent. What's my period? 3. And then to find my vertical asymptote, I take what's with cotangent, which is 3x minus pi. And set equal to my initial asymptote, which is pi. So I need to solve for x. What should I do first? Add the pi. Since we don't have a fraction, we don't have to worry about any common denominator stuff. So it's pi plus pi. 2 pi. And then to finish solving for x. Okay. So there's our vertical asymptote. So that means this value in between here, roughly somewhere in this 2 pi. Okay. Now I will say, in neither one of my examples this happened, but every once in a while, with cotangent, since its initial period is pi and the initial period is initial vertical asymptote also is at pi, it is occasionally possible for your period to match your vertical asymptote because they're both starting at pi. So that can happen every once in a while. This one was 2 pi over 3, it was close, but again, it's not quite the same. So again, it is possible, it does happen every once in a while, that the period for cotangent can match the vertical asymptote. Okay. So that's where we're going to stop. We're going to do the other 2 graphs later. So I'm going to go ahead and post an assignment for you. I think I already did this one. There are 8 graphs. Now, with this one, since it's a lot of solving work, I kind of prefer you to snip the graphs and then either print it and then do the writing on it, or snip the graphs and do your work on a separate sheet of paper and then turn it into the basket. That's usually how I prefer it, because when you're solving, it's hard to show the work on the computer slide. But again, I kind of leave it up to you whether or not you want to have the graphs with your work. So, like I said, some people have done that, and I actually like it quite a bit. So again, just print out what you have, and then write the stuff next to it. That works. Or, like I said, if you don't want to print, that's okay too. But do your snips online, and then do your period and vertical asymptote for each one on notebook paper. That either way works. That's what I prefer. That makes sense.
Most of us are going to be gone tomorrow, so let's just have it tomorrow.
Tomorrow we are going to work on this and test it. And most of you didn't miss that much, so you don't have much to make up for test. Okay. Everyone good to go? Stop.